In the last unit, we talked about what electricity is and how it flows through a circuit. And now we're going to look at circuits more closely and examine the different ways that the components in a circuit can be arranged. As we move on through this unit, we'll cover the concept of power, and then we'll go into a little more detail about magnetism, because magnetism has a lot to do with how most generators operate. And finally, we'll get to AC, alternating current. Almost all the equipment in your plant operates on AC. Well, the first thing we're going to talk about is circuits, series circuits and parallel circuits. The cells in your plant's battery are connected in series, but most of the plant's equipment is connected in parallel. You need to know how circuits work before you can understand how they are used in your plant. Now, a series circuit is a circuit with a single current path. The components in a series circuit are all connected one after another. A parallel circuit is made up of two or more parallel branches. The branches split away from the main circuit and then join the main circuit again at some point farther along the way. Each branch may have a different resistance and therefore a different current. It is also possible to combine series and parallel arrangements into one circuit. Well, in this circuit, resistors are set up both in series and in parallel. You can apply the concepts we cover about series circuits and parallel circuits to combined circuits as well. Now that we've seen how series circuits and parallel circuits are arranged, let's look at how they work. In a series circuit, there is only one current path. Okay? And this means that all devices in the circuit have to be either on or off at the same time. A parallel circuit is different because the current flows through several branches. It is possible to have some devices off while others are on. You can see what I mean here. Anytime one of the light bulbs in this series circuit burns out, there's a break in the current path and the circuit is interrupted. So current flow stops. But in this parallel circuit, it doesn't matter if one or two bulbs burn out. There's still a complete path here in this branch where current can flow, so there's still power to the third bulb. The major difference between series circuits and parallel circuits is in how voltage and current are distributed. First, let's look at how voltage is distributed in a series circuit. This is a series circuit. It only has one current path, and when the switch is closed, current can flow through the circuit. There's about ½ amp flowing through here. This black box is what we call a regulated power supply. It provides a more accurate voltage than a battery. The switch on the black box turns the power off and on. The resistor in this circuit has a resistance of 10 ohms. In a circuit like this with only one resistor, the amount of voltage across the resistor is always equal to the source voltage. Now, in this circuit with the regulated power supply, the source voltage is known. It's 5 volts. We'll have to measure the voltage across the resistor. And when we hook up the voltmeter, we see that the reading is 5 volts. Another way to say that the voltage across the resistor is 5 volts is to say that the voltage drop in this circuit is 5 volts. Now, the term voltage drop may sound like we lose some voltage somewhere along the line, but that's not the case. In the circuit we just looked at, the voltage across the resistor was equal to the source voltage. We didn't lose any. The term voltage drop refers to how voltage is distributed in a circuit. Well, what happens if we have more than one resistor in a series circuit? Let's go back to our circuit here and replace the 10 ohm resistor with two 5-ohm resistors. First we cut the power, and then we will put in the new resistors. There's a 5, remove the 10, and put in another 5. Now, we said earlier that the amount of voltage across a single resistor in a series circuit is always equal to the source voltage. In a series circuit with 2 or more resistors, the voltage drop across each resistor is always in direct proportion to the resistance of that resistor. The only thing that's changed in this circuit is the number of resistors. The source voltage is still 5 volts. Now let's turn the switch back on and measure the voltage across each of the 2 resistors. Okay, the voltmeter shows that the voltage across the first resistor is 2.5 volts. And the reading on the second resistor, it's 2.5 volts also. So we were right. The voltage drop across each resistor is in direct proportion to the resistance of that resistor. Well, can we assume from what we just saw that the sum of the voltage drops across all the resistors in a series circuit is equal to the source voltage? If so, then the total resistance in a series circuit is equal to the sum of the individual resistances. Well, let's check this idea out. With one 10-ohm resistor, the current in this circuit was ½ an amp. Now we have two 5-ohm resistors. The source voltage is still 5 volts, and according to Ohm's law, which relates current, voltage, and resistance, if voltage and resistance don't change, current won't change either. If the total resistance in the circuit doesn't change when we replace one 10-ohm resistor with two 5-ohm resistors, then the current in this circuit should still be ½ an amp, and it is. Well, let's look at this same idea another way. Ohm's law tells us that current, I, equals voltage, E, over resistance, R. In the first circuit, we put in 5 for E and 10 for R. And then we can figure current as 5 over 10, or 1/2. In the second circuit, we add the resistances of the two resistors. 5 ohms plus 5 ohms equals 10 ohms. We have the same fraction, 5/10 for the E over R part of the Ohm's law equation, so current is still 1/2 amp. Now, that's the reading we got on the ammeter, so we've proved our point. In a series circuit, the total circuit resistance is equal to the sum of the individual resistances. This is true no matter how many resistors there are in a series circuit. Let's cut the switch here and add a 10-ohm resistor to this circuit. All right, we'll put it right in here. And now, what we have is 3 resistors in the circuit. R1 has a resistance of 5 ohms, R2 has a resistance of 5 ohms, and R3 has a resistance of 10 ohms. Now we'll activate our switch here, and with these 3 resistors, the total resistance in the circuit is 20 ohms because 5 plus 5 plus 10 equals 20. We haven't changed the source voltage. It's still 5 volts. But since the resistance has changed, current will be different. The ammeter shows us that the current is now 1/4 amps. Now let's use the voltmeter again to make sure that the voltage drop across each of these 3 resistors is in direct proportion to the resistance of that resistor. Okay, reading on R1 is 1 1/4 volts. We take a reading on R2. We also get 1 1/4 volts, and we have 2.5 volts left, so the voltage drop across R3 should be 2 1/2 volts, and it is. In each case, the voltage drop across a resistor is proportional to the resistance. Now, the other things we've covered about series circuits are also evident here. The sum of the individual resistances, 5 plus 5 plus 10, does equal the total resistance in the circuit, 20 ohms. And the total voltage drop across the resistors does equal the source voltage. Well, we haven't really talked about how current behaves in a series circuit, but we can cover it in a single statement. Because a series circuit has only one current path, Current is the same through all the components in the circuit. Parallel circuits are different, as we'll see in the next segment. Well, why don't you take a few minutes now to read through the material on the series circuits in your text, and if you have any questions, talk them over with your instructor. Parallel circuits are a bit more complicated than series circuits. Instead of just one current path, there may be many, and each may have a different resistance. We can sum up what you need to remember about parallel circuits in three basic facts. First, the voltage across each branch of a parallel circuit equals the source voltage. Second, the total current in the circuit is equal to the sum of the currents in each branch. And third, the total circuit resistance is less than the resistance in any of the branches. And it takes a lot more time to learn these facts than it does to say them. Let's look at this parallel circuit for a minute and think about how it works. It's not too different from this mechanical system. The pump provides pressure to each of the branches in this system, just as the voltage source does here. The throttle valves provide resistance to the water flow, just as the light bulbs provide resistance to the current flow. We can shut off water flow through some of the branches in the mechanical system by closing their throttle valves. Water continues to flow through the branches whose throttle valves are open. In the electrical circuit, we can switch off current through some of the branches without interrupting the others. In the mechanical system, the total water flow is equal to the water flow in all of the branches added together. In the electrical circuit, the total circuit current is equal to the current flow in all of the branches added together. Let's go back now to the three facts I gave you about parallel circuits and see how they work out in actual practice. Now, here's a schematic of the circuit we'll be using. The black box is the voltage source, 5 volts. Each resistor is labeled 10 ohms. According to the first of our three facts, the voltage across each branch of the parallel circuit equals the source voltage. Now, we can check that out with a voltmeter. First, we'll take a reading on the first resistor. And the meter reads 5 volts. It's the same as the source voltage. How about the resistor on the other branch? Okay, the meter reads 5 volts here too. Okay, that proves our first fact. The voltage across each branch of a parallel circuit does equal the source voltage. Let's move on to the second fact. The total current in a parallel circuit is equal to the sum of the currents in each branch. Now let's figure out what the current should be and then take some measurements to see if we're right. We'll use Ohm's law. I equals E over R. But since we have two branches in our parallel circuit, we'll call the current in the first branch I1 and the current in the second branch I2. We only need one E because the voltage is the same across each branch. We'll call the two resistors R1 and R2. So to find the amount of current in the first branch, we divide E, which is 5 volts, by R1, which is 10 ohms, and we get a value of 1/2 amp for I1. Since R2 is 10 ohms, just like R1, we have a current of 1/2 amp flowing through the second branch too. And according to what we've said, we can add I1 and I2 to get the total current. We can expect the total current flow in this circuit to be 1 amp. Well, let's open the switch and hook an ammeter up to each branch, and we will see what we get. Okay. For the first branch, the meter reads 1/2 amp. So we'll open the switch, reconnect this, and take a reading on the second branch. And the second branch also reads 1/2 amp. The ammeter on our power source reads total current 1 amp. Now, fact 2 checks out on paper and in practice. Now for the last of our three facts. The total circuit resistance is less than the resistance in any of the branches. We need Ohm's law again to see why. According to Ohm's law, R equals E over I. Total resistance equals the source voltage divided by the total current. In the circuit we've been using, the source voltage is 5 volts and the total current is 1 amp. The total resistance then is 5 divided by 1, or 5 ohms. Now we know that each of the two resistors in the circuit has a resistance of 10 ohms. So the total resistance is less than the resistance in any of the branches. Now, we can check the total resistance reading with an ohm meter. See what we get. Closing the switch. We were right. It is 5 ohms. Now, before we leave parallel circuits, there's one more thing you should know about them. Whenever you add another load in a parallel circuit, total resistance goes down, so total current goes up. Let's add another branch to this parallel circuit and see what happens. Okay, the third resistor here has a resistance of 10 ohms, just like R1 and R2. We still have the same source voltage, but we've changed the current flow by adding the third branch. Ohm's law tells us that I3 equals E over R3, so the current in the third branch is 5 volts divided by 10 ohms, or 1/2 amp. With 3 branches in the circuit, the total current in the circuit is 1/2 plus 1/2 plus 1/2, or 1.5 amps. We added another load to the circuit, and the current went up. Now that we know the total current for the 3-branch circuit, we can figure the total resistance. R now equals the source voltage, 5 volts, divided by the total current, 1.5 amps. So the total resistance in this circuit is now 3 1/3 ohms. The added load made the total current go up, but the total resistance went down. Just to double check, let's take 2 more measurements. Okay, first, the total current. The meter reads 1.5 amps, so we were right on that one. The current increased from 1 amp to 1.5 amps when we added the third branch. Now, for the total resistance, if we get a reading of about 3 1/3 ohms, we were right about the total resistance going down when we added the third branch. Well, close the switch. Well, there's the reading, 3 1/3 ohms. We'll be getting back to parallel circuits and circuit loading later on in this unit, so why don't you take a few minutes now to read over the material in your text. If you have any questions, clear them up with your instructor before we go on. So far, we've been talking about what electricity is and how it moves through circuits. But we haven't really talked about how electricity is used. When we talk about using electricity, we talk about power. And power is the subject of this segment. We'll see just what power is and how it's affected by voltage and current. We'll also look at how power is measured and how it's distributed in series circuits and in parallel circuits. That's important because it's the first step in understanding how loads affect your plant's generators. Let's begin by defining power in terms that you're familiar with. Power is a measure of the rate at which work is done by electrical energy. It's voltage times current. Voltage provides force, and current provides rate and motion. Remember, in Unit 1, we said that current is measured in terms of the number of electrons that pass by a given point in 1 second. So current is actually the rate at which electrons move. You need both voltage and current to have power. To find out how much work is done, that is, how much power is used, you multiply the voltage times the current. Well, let's get some numbers from this circuit to do a power calculation. The source voltage here is 5 volts, and the ammeter shows us that the current through the circuit is 1 amp. We don't really need to be concerned about the resistor in this circuit because it isn't a direct part of the power formula. Of course, you know that resistors affect the current in the circuit, but we're getting our current reading directly from the meter. We don't have to calculate it this time. Okay, to find out how much power we have, we multiply the voltage, 5 volts, by the current, 1 amp, and we get 5 units of power. They are called watts. Power is measured in watts. When we talk about using power, though, we usually need something more than just watts. We use power over a period of time, so we need a time unit to go with the power unit. The basic unit for power use is the watt-hour, but you might be more familiar with the term kilowatt-hour. That's the way the power used in your home is measured. And that's the unit you see on your electric bill. 1 kilowatt-hour is equal to 1,000 watt-hours. The meter attached to your home is calibrated in kilowatt-hours. It records the amount of power used in your home. The power company reads the meter and bills you for the amount of power you've used since the last time the meter was read. For example, let's say that your meter shows that you've used 2,000 kilowatt-hours this month. You'll get a bill charging you for 2,000 kilowatt-hours at the power company's present rate. Your home's power meter uses kilowatts, but the meters connected to the generators in your plant probably use much larger units, megawatts, that is, millions of watts. These meters have a different purpose than home meters too. The meters on your plant's generators are used to indicate how many watts of power are being produced. They show the loads on the generators. It's important not to overload a generator. In that sense, they're just like people. If you ask them to do more than they're able to do, they'll overwork and break down. Loads are added onto a generator in 2 ways, in parallel and in series. Parallel loads are the most common. Parallel circuits are used to wire almost everything in homes and industries today. But you have series loads in the plant too. The DC motor starters, for example, are in series with their motors. Let's look at how power is distributed in series circuits and in parallel circuits. As I said earlier, that's the first step in understanding how loads affect your generator. We'll start with series circuits. This one has 2 5-ohm resistors in series. The source voltage is 5 volts and the current is 1/2 amp. To find the power in the circuit, we multiply voltage times current. 5 times 1/2 is 2.5. We have 2.5 watts of power in this circuit. The next thing we want to find out is how much power each of the resistors in the circuit used. If we use the same formula, power equals voltage times current. P equals EI. But we have to be careful. The voltage we need now is the voltage across each individual resistor, not the source voltage. We can use Ohm's law to calculate that voltage. Ohm's law tells us that voltage is equal to current times resistance. E equals IR. We know that in a series circuit, the amount of current flowing through each resistor is the same as the total current in the circuit. The total current in this circuit is 1/2 amp, so we can use that value for I. Since we're using known resistances, we know that each resistor, R1 and R2, has a resistance of 5 ohms. The voltage drop across each of the 2 resistors then is 1/2 amp times 5 ohms, or 2.5 volts. Now that we know both voltage and current, we can calculate power. The power used by each resistor is 1/2 amp times 2.5 volts. Working out the math, we see that R1 and R2 each used 1 1/4 watts of power. A few minutes ago, we calculated the total power in this circuit by multiplying the source voltage by the total circuit current. It was 2.5 watts. We get the same answer when we add the power used by R1 and R2. 1 1/4 watts plus 1 1/4 watts equals 2.5 watts. Both of these methods work for series circuits. To find the total power in a series circuit, You can either multiply the source voltage by the total circuit current or add the power used by each device in the circuit. The results are always the same. Now, these two methods work for parallel circuits too, but you do the figuring in a different way. Since power is voltage times current, let's review what we know about voltage and current in parallel circuits. We know that the voltage drop across each branch is equal to the source voltage, and we know that the total current in the circuit is equal to the sum of the branch currents. Our first method for figuring power is to multiply the source voltage by the total circuit current. We can find the total circuit current by figuring the current through each resistor in the circuit and then adding all those branch currents together. This circuit has 3 resistors to act as loads. R1 has a value of 10 ohms, R2 has a value of 10 ohms, and R3 has a value of 5 ohms. The regulated power supply gives us a source voltage of 5 volts. We'll use Ohm's law to get the current for each branch. I equals E over R. So the current for the first branch with R1 is 5/10 or 1/2 amp. R2 is the same as R1. So the current for the second branch is also 1/2 amp. For the third branch, the current is 5/5 or 1 amp. To get the total current in the circuit, we add the current in the 3 branches. 1/2 plus 1/2 plus 1 equals 2 amps. The total power in the circuit, E times I, is 5 volts times 2 amps equals 10 watts. Our second method for finding the total power used in a circuit is to add the power used by each device. In a parallel circuit, the voltage drop across each branch is equal to the source voltage. So the voltage across each resistor is the same, 5 volts. We just figured the current in each branch, so we have everything we need to get the power used by each resistor. Our basic formula for power, as always, is voltage times current. R1 is 5 volts times 1/2 amp for 2.5 watts. R2 is also 5 volts times 1/2 amp, again, 2.5 watts. R3 is 5 volts times 1 amp for 5 watts. When we add 2.5 watts plus 2.5 watts plus 5 watts, we get 10 watts for the total power in the circuit. That's what we got with our first method too. We can use either one from now on whenever we want to find the total power in a circuit. Now, back in segment 2, we saw that the total current in a parallel circuit increases when branches are added. Since power is voltage times current, increasing the current also increases the power. This schematic will help you see how this works. This circuit is the one with 3 resistors that we've been using. This one has another resistor added to it. We've added another load in parallel. Now, the source voltage for each circuit is 5 volts. We've already seen that the total current in the first circuit is 2 amps and the total power is 10 watts. In the second circuit, we've added a 5 ohm resistor, so we have another amp of current flowing through that branch. That means total circuit current is now 3 amps, and the total power in the circuit is up to 15 watts. Because our schematic shows the power used by each resistor, we could also find the total power by adding those values. As you know, we get the same answer both ways. There's another way to calculate power that we haven't talked about yet. It's a shortcut that lets you figure out power without knowing what the voltage is. The formula for this method is power equals current squared times resistance. P equals I squared R. Before we look at how this formula works, let me show you where it comes from. We know that power equals voltage times current. P equals EI. From Ohm's law, we also know that voltage equals current times resistance. E equals IR. So we can write the formula for power the first way, P equals EI, or this new way, P equals IR times I. because E and IR both equal voltage. Power equals voltage times current, or power equals current times resistance times current. To put it briefly, power equals current squared. That's another way of saying times itself, times resistance. P equals I squared R. Now let's try out our new formula with some numbers. In this circuit, we have our 5-volt power source and a 2-ohm resistor. That means that the current flowing through the circuit is 2 1/2 amps. I equals E over R. And 5 divided by 2 equals 2 1/2. The first formula for power is P equals EI. So power is equal to 5 volts times 2 1/2 amps, or 12 1/2 watts. If we use the second formula, P equals I squared R, we get the same answer. 2 1/2 squared, or 2 1/2 times 2 1/2, is 6 1/4. And 6 1/4 times 2, again, gives us 12 1/2 watts of power. Your text has some problems that you can work out using either or both of these formulas. Why don't you read through your text now and make sure that you know how to use the formulas to figure out what the power is in both series and parallel circuits. If you still have questions, discuss them with your instructor. Back in Unit 1, we looked at 6 ways of producing electricity. One of these was magnetism. We used magnetism and relative motion to produce a voltage, and then we used that voltage to produce a current. We also saw that when we sent current through a wire, a magnetic field developed around the wire. We need to go into more detail on magnetism and magnetic fields than that, though. So magnetism, of course, is the key to understanding how most motors and generators work. We'll be talking first about what magnetism is. It's a force. In fact, it's a field of many small force lines joined together. Like gravity, it's invisible. Although you can't see the force of a magnetic field, you can see its effect on certain materials. I'll be showing you this effect in a few minutes. We'll be talking about magnetic properties, too. You need to know what magnetic properties are so that you can understand how magnets and magnetic fields behave. Only certain materials have magnetic properties. Centuries ago, in a town called Magnesia, someone discovered an unusual stone that attracted iron. This was a pretty interesting characteristic, so they kept experimenting with the stone. Eventually, someone discovered that if you tied a bit of string around the stone and let the stone hang free, the stone would line itself up with north and south. They called the stone a leading stone, or a lodestone. It was a natural magnet, and what they made with it was the first compass. Now, we don't need to hunt for lodestones anymore. We can make our own magnets. You know the sets of magnets they sell as toys for kids to play with? Well, they're made of inexpensive metals that can be magnetized. Only a few types of metals, like some forms of iron, nickel, and cobalt, can be made into magnets. In these metals, the atoms behave in a special way that allows the metal to be magnetized. The atoms combine to produce areas in the metal called magnetic domains. And these magnetic domains act like lots of tiny magnets in the metal. When the metal is in an unmagnetized state, the magnetic domains are arranged every which way. The magnetic forces of the domains cancel each other out. Now, suppose something happens to rearrange the magnetic domain so that they're all facing the same direction. Then, instead of canceling each other out, the magnetic forces combine to form one big magnet. As soon as this happens, the metal is magnetized. Let's look at what happens in a piece of iron. These are the magnetic domains. They're facing in all different directions, so the force of each domain is canceled out by the others. But if we stroke the piece of iron with a magnet, all the domains begin to line up in the same direction. As they do, the forces of all the domains start acting together and the result is a magnetic field. A magnetic field is actually a series of lines of force or lines of flux that flow from one end of a magnet toward the other end. The ends of a magnet are called poles. One end is the North Pole and the other end is the South Pole. As more and more magnetic domains line up in the same direction, more and more lines of force flow from one pole of a magnet to the other. The lines of force are also closer together when there are more of them. And the closer the lines of force, the stronger the magnetic field. With fewer lines of force, the lines are farther apart, and the magnetic field is weaker. Let's stop here for a minute and review what we've said so far. We said that some metals can be magnetized because they contain magnetic domains. When the magnetic domains are made to line up in the same direction, the forces of all the domains act together to produce a magnetic field. Now, the force of a magnet comes from its magnetic field. As we said, that field is actually made up of lines of force. These lines flow from one pole of the magnet to the other on the outside of the magnet, and they complete the loop on the inside. The term pole is just a convention. Because magnets have the power to do two things at once, attract and repel, they are said to have polarity. Polarity in a magnet just means opposite powers are contained in the magnet's two ends. Now, like magnetic poles repel each other, and unlike magnetic poles attract each other. You can see what I mean as I move these two magnets around. Now, like poles repel and unlike poles attract. To indicate what's happening in a magnet, the terms North Pole and South Pole are used to identify the two ends. Lines of force always flow from the North Pole to the South Pole on the outside of a magnet. Okay, that's enough facts for right now. Next, we're going to work with some simple magnets to demonstrate some of the effects of a magnetic field. Now, this magnet is made of steel. It will attract some of the items on the table, but not all of them. I have lots of different things here, everything from paper clips to a piece of rubber. As you can see, the magnet only attracts the other metals, and that's because these metals also have magnetic properties. We can see the attraction here, but it would be better if we could actually see the effects of the lines of force. Now, setting them up is a little more complicated, but to show you the effects of lines of force, I'm going to set this magnet on a block of wood and then put this piece of plexiglass over it. And these are iron filings. And when I sprinkle the iron filings on the glass, you'll be able to see the effects of the lines of force because the iron filings will line up with the force field. We can even increase the size of a force field by placing a piece of steel next to the magnet. Steel and certain other metals can add to the power of a magnet by becoming temporary magnets themselves. Now you can see what I mean right here. This magnet can't pick up this nail because they're too far apart. Now, look what happens when I put this steel bar between the magnet and the nail. The nail is picked up. And as long as this steel bar is in contact with the magnet, the steel is magnetized and it attracts the nail. When I remove the magnet, the nail drops off of the steel bar. Now, I can make this paper clip a temporary magnet too. It's not a magnet now. You see, it won't pick up another paper clip. But I can magnetize it temporarily by stroking it against this magnet. And now it will pick up the other paper clip. A temporary magnet doesn't keep its magnetic properties for very long. It soon becomes demagnetized. The ability of some metals to become temporarily magnetized is used in some specific applications in your plant. Relays and solenoids, for example, use temporary magnets. We'll see how when we get to the last unit in this topic. Other metals can become permanent magnets. When one of these metals is magnetized, the domains stay lined up for a very long time. Now, the toy magnets that I mentioned earlier are permanent magnets. You can use them for years and they keep on working. Most of the magnets in your plant are a bit different, though. We call them electromagnets because their action is controlled by switches. You can turn them on and off. We'll talk about electromagnets in the next segment. First, though, read through the material on magnetism in your text and make sure you understand what we've covered so far. Electromagnets have many uses in your plant. You'll find them in generators, motors, relays, solenoids, and other plant equipment. The main advantage that electromagnets have over the simple magnets we looked at in the last segment is that electromagnets can be controlled. Now, in Unit 1, we said that every time you send current through a conductor, you get a magnetic field around that conductor. Well, it's possible to create that magnetic field when it's needed by using an electromagnet. With an electromagnet, you can turn the magnetic field on and off, and that's what I mean by a controllable magnet. There's no switch on a permanent magnet. I'm going to use this circuit right here and this compass to demonstrate how an electromagnet works. Right now the switch is open, so no current is flowing through the circuit. The compass needle is pointing north, like most compass needles, because of the Earth's natural magnetic field. The circuit is set up so that the wire runs parallel to the compass needle. As soon as I close the switch, current will flow and a magnetic field will build up around the wire. Now, since the magnetic field around the wire is closer to the compass needle, and therefore stronger than the Earth's magnetic field, we can expect the compass needle to move. The needle changes direction so that it points to the current-carrying wire. Now, let's close the switch and see what happens. Yep. The compass needle did just what we thought it would. It's pointing to the wire. Now, this is what the magnetic field around the current-carrying wire looks like. The compass needle is aligned with the magnetic field. It shows us which way the magnetic field is flowing. Now, there's a rule you can follow so that you'll always know which way the magnetic field will flow. You can use this rule instead of a compass. It's called the left-hand rule, and it'll come in handy when you're studying motors and generators. It's an easy way to remember the relationship between the direction of the magnetic lines of force around a conductor and the direction of current flow. The left-hand rule works like this. Imagine that you're holding the conductor in your left hand with your thumb pointed in the direction of the current flow. Your curled fingers are then pointing in the same direction as the magnetic lines of force. This graphic shows it better than I can. The fingers are in a position that represents the magnetic field. The lines of force that make up the magnetic field rotate around the conductor in a complete circle that's constant. Current flow is constant too. Current always flows from negative to positive. What we're really saying here is that we can depend on current and a magnetic field to always behave in a specific way in relation to each other. Now, we can prove it by reversing the direction of one of them and seeing what happens. Now, if we reverse the battery connections in this circuit, we reverse the flow of current, right? Current still flows from the negative terminal to the positive terminal. But now it moves through the conductor in the opposite direction. Look what happened to the compass needle. It reversed its position. It's pointing in the opposite direction too. So the left-hand rule holds true. Well, so far we've established that we can control the magnetic field around a current-carrying conductor. We can start and stop it by starting and stopping the current flow. And we can change its polarity by changing the electrical polarity of the circuit, just like we did. We can also control the magnitude of the magnetic field around a current-carrying conductor. There are three ways that we can increase the magnetic field around this conductor. Because the magnetic field will increase in the presence of a stronger current, the first way is just to increase the current flowing through the wire. The second way to increase the magnetic field is to form the wire into a coil. When we do that, the magnetic fields around each turn of the wire add together and form one large magnetic field. The more turns you put in the coil, the stronger the magnetic field. We can strengthen this magnetic field even more if we put an iron bar in the center of the coil. As we saw earlier, the iron will become a temporary magnet. By replacing some of the air in the center of the coil with iron, which becomes a temporary magnet, we can indeed strengthen the magnetic field. The three main factors that determine the strength of an electromagnet, then, are the amount of current, the number of turns in the coil, and the material in the center of the coil, what we call the core material. The combination of the first two factors, that is, current and the number of turns in the coil, is called ampere turns. The term just means that if you multiply the current in amperes flowing through the conductor by the number of turns in the coil, you get the field strength of the electromagnet. It works like this. In this electromagnet, the current is 1 amp and the coil has 100 turns. If we multiply 1 amp by 100 turns, we get 100 ampere turns. In this electromagnet, the current is 10 amps and the coil has 10 turns. When we multiply 10 amps by 10 turns, we again get 100 ampere turns. In both cases, the number of ampere turns is the same and the strength of the field is the same. We're going to see current and magnetism in action in the next segment. But before we go on, let's stop for a few minutes so you can review what we've covered about electromagnets. Up to now, we've been discussing electricity primarily in terms of a one-way flow of current, what we call direct current, or simply DC. From time to time, I've mentioned that we'll be getting around to alternating current, AC, later. Well, later has finally come. In this segment, our subject is alternating current. We'll talk about what AC is, how it flows through a circuit, and how a simple AC generator works. Let's begin with what AC is. It's current that flows in one direction and then reverses and flows in the opposite direction. Alternating current gets its name from the fact that it flows alternately in two directions. Well, the logical question here is, why does it do that? Well, the answer is that in AC, the polarity of the power source changes, so the current changes direction. Now, the polarity of the power source sounds like a heavy-duty phrase, but it really isn't. It's just a brief way of referring back to the fact that current always flows from the negative terminal of a power source to the positive terminal. This is true for both direct current and alternating current. The difference is in the type of power source used. The power source for DC has a fixed polarity, so current always flows in one direction. But for AC, the polarity of the power source constantly changes. As the polarity of the power source changes, the direction of the current flow changes with it. Now, before we start looking at how a simple AC generator works, I want to mention two conventions that are almost always used when you're dealing with alternating current. The first convention is the use of a curve, like this one, to indicate the way that AC changes directions. The plus sign indicates one direction, and the minus sign indicates the opposite direction. As I said, this is the conventional way of representing the flow of alternating current. The second convention is the use of degrees. Most AC power sources have a moving part. As you know from our discussion of magnetism, we can get a current if we induce a voltage. To induce a voltage, we need a magnet, a conductor, and relative motion. In many cases, like the model you see here, the moving part rotates, that is, it goes around in a circle. A circle contains 360 degrees. The convention, then, is to use degrees to indicate where the moving part of the AC power source is in its rotation. Now, if we assume that the rotation starts at 0 degrees, the moving part will reach 90 degrees when it has rotated 1/4 turn. When the moving part is halfway around the circle, it is at 180 degrees. When it reaches the 3/4 mark, it's at 270 degrees, and at the end of one full rotation, it's back at 0. On this power source, we can call the whole circle a complete cycle. The most typical AC power source is an AC generator or an alternator. Our AC generator here is a very simple one. It's connected to a light bulb so you can see the effect of alternating current at work. We'll also look at how alternating current is plotted or drawn on paper. Now, I keep stressing that we're talking about AC power and AC generators because we've been using terms like power and current without saying specifically whether we were talking about AC or DC. From now on, we'll be talking about both types of currents, so we'll identify each as we go along. Oh, by the way, practically all of the electricity used today is AC because it's cheaper than DC to produce and distribute. Now here we have the parts of a simplified AC generator: a loop of wire, a stationary magnet, a pair of slip rings, and a set of brushes. It's set up like this. The loop of wire is our conductor. It's placed between the poles of the magnet. Each end of the loop is connected to a slip ring. When the generator is working, the slip rings slide against the brushes. The brushes transmit current from the slip rings into this electrical circuit. In our generator, the slip rings are made of metal. The brushes are made of carbon, a material that can maintain good sliding contact with the rings. This is our AC power source for the moment. We'll be using magnetism to induce voltage. We have a magnet and a conductor. We need relative motion. To induce voltage, we can do one of two things. We can move the magnet in our generator through the loop of wire, or we can move the loop of wire between the poles of the magnet. The point is that either the magnet or the loop of wire must be moved. In our generator, the magnet is stationary. It's not going to move. Since either the magnet or the conductor has to move, we have the conductor, the loop of wire, rotating between the poles of the magnet. Now, since we have a magnet, a conductor, and relative motion, we can induce voltage. As I move this conductor in one complete rotation, it's cutting through the magnetic field, right? You know that the magnetic field is made up of lines of flux that always move in this direction. But each part of our loop of wire cuts through these lines in two different directions. From here, 0 degrees, to here, 180 degrees, this part of the conductor is cutting downward across the lines of flux, while this part of the conductor is cutting upward. From here, 180 degrees, back to here, 0 degrees, the motion is reversed. The part of the conductor that was cutting downward across the lines of flux is now moving upward, and the part that was moving upward is now cutting downward. Earlier, we said that the polarity of an AC power source reverses. Well, the reversal takes place here, when the direction in which each part of the conductor cuts across the lines of flux changes. In this direction, current flows from here, the negative terminal, to here, the positive terminal. And then at this point, the flow of current stops. When the voltage reverses, current flows in the opposite direction. The current is still flowing from negative to positive, but the negative and positive positions have reversed. So the actual direction of current flow also reverses. The position of the conductor in relation to the lines of flux also determines how much voltage you have at any given point. When the conductor is in this position, it's cutting through the fewest flux lines, so it puts out almost no voltage. But in this position, it's cutting through the maximum number of flux lines, so it's putting out the maximum amount of voltage. Let's look at the way the voltage produced during the movement of the conductor appears on paper. Earlier, we saw a sketch of how alternating current flows. Well, we can plot AC voltage and get the same kind of curve. The kind of curve we have here is called a sinusoidal curve, a sine curve, or a sine wave. It has no sharp bends or straight portions, just a smooth rise and fall. The AC voltage starts at the 0 point on the sine curve, corresponding to 0 degrees for the position of the conductor at the beginning of its rotation. the voltage increases to a peak positive value at 90 degrees. That's the point where the conductor cuts through the maximum number of flux lines. Then the voltage decreases to 0. At that point, 180 degrees, the conductor is cutting through the minimum number of flux lines because it's moving parallel to them. As the conductor starts to move from 180 degrees to 270 degrees in its rotation, it cuts through the flux lines in the opposite direction, and the voltage starts to increase again. It reaches its peak negative value at 270 degrees. The voltage then decreases again until at 360 degrees it returns to 0. Here, the position of the conductor is parallel with the flux lines, just as it was at the beginning of the cycle and at the 180-degree point. Later on, we'll talk more about these peak values that you see on the graph. Right now, though, let's try to put together all of the facts we have about alternating current and get a feel for how it actually works. We have a circuit hooked up to the terminals of this AC generator so that we can see the effect of the voltage and current. As the generator turns, voltage and current build up to a peak positive value and then decrease to 0. At this point, current and voltage reverse direction and build up to a peak negative value. Then they decrease to 0 and the cycle is complete. During each cycle, the current flowing through the bulb causes it to brighten, dim, go out, brighten, dim, and go out again. This cycle is repeated 60 times per second in a typical power system. It's so fast that even though the bulb is actually turning on and off, it looks as though it's on all the time. Before we start in on cycles and time, let's look at our voltage graph again for a minute. We used the term peak value before. The peak value occurs twice in each cycle, right? One positive peak and one negative peak. Well, on this graph, each peak value is 10 volts. Peak values aren't used very often. Most of the time, we talk about effective AC values. Let's take a common example to show you what I mean. A 100-watt light bulb doesn't work as well in a circuit with 120 volts peak AC value as it does on 120 volts DC. As we just saw in our simple circuit, the bulb with AC is off part of the time. Because of this, the total amount of light is less than it would be with DC. With DC, the bulb is always on. It's because alternating current does not remain at a peak value that peak values are not generally used. Instead, scientists have come up with a way to find out the exact difference between a specific AC value and a DC value with the same numbers, like the difference between 120 volts AC and 120 volts DC, for example. Through a number of experiments, scientists have found out that 1 ampere peak value of alternating current produces the same effect as 0.707 amperes of direct current. This same relationship applies to voltage because voltage produces current. This effective value for AC is often called the RMS value. The letters stand for root mean square. And what it all means is that the effective value of AC is not the peak value. The effective value is the square root of the average or mean of the square of the current. The mathematical formula doesn't concern us here. What's important is that when we talk about AC, both current and voltage, we use effective values, that is, RMS values, instead of peak values. Now, once the RMS system was established, RMS values were used instead of peak values to rate AC operating voltages on everything from industrial equipment to power lines. You can take it for granted that the rating of an AC motor is the RMS rating, unless the data plate on the motor says otherwise. Okay, that rating refers to the effective value of the voltage and current. Now, let's talk about the rate at which AC cycles are completed. That's what we call frequency. Frequency is a term you'll only use with alternating current because that's the only time you're dealing with cycles. For a long time, frequency was only expressed as cycles per second, or CPS. Today, however, a more common term is hertz. 1 hertz is equal to 1 complete voltage cycle per second. Well, that's all we have to say about AC for now. We've looked at a simplified AC power source. We saw how it affects current flow. We also saw how a sine wave is plotted on a graph. And we covered some of the terms that are peculiar to AC: peak values, RMS values, and frequency. Earlier in this unit, we talked about series circuits and parallel circuits and the ways in which current and voltage are distributed. Then we covered power and the power formula, and we went into a lot more detail on the subject of magnetism and electromagnets. You're well on your way now to building the solid foundation that you'll need to understand how the complex equipment in your plant works. Read the material in your text about alternating current. Make sure you understand everything we've gone over. If you still have questions, discuss them with your instructor.